So my recording stopped before, but we were up to the second step in the fill in the blank proof. Angle A being congruent to angle B, because if two sides of a triangle are congruent, the sides opposite are congruent. And then we have our next piece of given information, that angle CAD is congruent to angle CBD. And I didn't put the third piece of given information there because I see that that's down here in step number 7. And if you were writing your own proof, you could definitely put all the givens in one step at the beginning. In this fill in the blank proof, it's broken up because, as you can see from the first given's written, and then step 2 is the conclusion that comes from that given. So the structure of this proof is that they're writing each given, and then the conclusion that comes from that given. And that's a good way of writing proofs as well. That way you make sure you don't miss any givens also. Either way works. And then we were talking about the subtraction, and that's provided to you here. So now we have to figure out what the subtraction leaves us over with. We said that the subtraction leaves us over with the two angles in blue inside the triangles. Angle DAE congruent to angle DBE. And that's by substitution, because the subtraction of the angles gives us those two angles. We're taking the big angle A, the big angle B. We're subtracting off the part that's congruent that's outside the triangles that we want. And we're being left over with the two angles in blue that are inside the triangles that we're proving congruent. Oh, wow. And it looks like this proof is being done differently in the fill in the blanks than how we marked it. And this is why fill in the blank proofs are often harder than regular proofs that you write yourself, because you might see a way to do it. Like I saw angle, side, but in the fill in the blanks, it's done a different way. And then we kind of have to follow the logic there. So it looks like maybe the reflexive property is actually not going to be used here. So I'm going to delete that for now, because even though it's true, in this fill in the blank proof, following the reasoning that's provided here, it doesn't seem like that's given. That's being used, sorry. So now it's saying if angles of a triangle are congruent, the sides opposite are congruent. So that's coming from what we just proved here. So we just proved that the two blue angles, angle DAE and angle DBE, are congruent. Notice how those are two angles of the triangle ADB that I just highlighted in brown. I can draw that triangle over here so you could see it a bit more clearly what I'm saying. Here's ADB, and here are the two angles that we just now proved are congruent. So if two angles of a triangle are congruent, the sides opposite are congruent. That's the converse of the base angle theorem. So if I transfer those sides over here, we see from the triangle drawn separately, it's AD and DB. And you can also see it in the original diagram that I just marked, that it's AD and DB that are across from the congruent angles. Sometimes drawing the triangle separately can help you better see what's going on in it, because sometimes there's a lot going on in the diagram. Then our final given, that CE is perpendicular to AB. And from that given, we're going to put the conclusions that we drew about the right angles, because we did mark the right angles in the diagram, but that wasn't given to us. We were just given that the lines are perpendicular. So that's angle DEA and angle DEB are right angles, because perpendicular lines form right angles. And actually, now that the plan is different than what I thought, it might not be AAS. So we're going to have to go back, because that was when I thought we were using the reflexive property. It might still be, but it might not be. So we're definitely going to just double check. And then I'm going to say that the right angles are congruent, because all right angles are congruent. And we need that if we're going to be using anything with an A, like ASA, AAS, SAS. If we're using any of those, we need it because the A stands for congruent angle pair. The only one that we don't actually need that step for is HL. So if we end up using HL, then instead we would have to say that the triangles are right triangles, because for HL you don't need congruent angle pairs, you need to have right triangles, because otherwise you wouldn't have your H or your L. I'm going to just keep it as is, because angle side still applies. We have, let me circle what we have in yellow. We have the right angle, we have this blue angle, and we now have this side. So we do still have angle side. You could also write HL. The thing is, if you're going to write HL, and I'll just show you that really quick while we're on this video. For HL, actually, I'm not, because for HL, I do need a congruent leg, so I would need to use the reflexive property, which there wasn't a spot for in this proof. But if you were writing this yourself, you could definitely use HL with the shared side as your leg. You have the hypotenuse. And the only difference in what you have here is that instead of saying that the right angles are congruent, you would instead say triangle ADE and triangle BD are right triangles. Okay. Next proof. So we have parallelogram DEFG. So that's here. And it's a parallelogram. So everything we know about parallelograms applies. I don't want to go start marking everything because that's going to get confusing. So I like to take a look at the proof statement and see what's actually going to help me. Angle DGK is congruent to angle EFH. And we're proving that DK is congruent to EH. So DK is on this triangle, and EH is the side of this triangle. So ultimately, we need to prove these two triangles, DGK and EFH, congruent. So now when I'm looking for parallelogram properties in the parallelogram that I have DEFG, I'm going to look for parallelogram properties that are going to give me more information about those two triangles. We already have an A. Opposite sides of a parallelogram are congruent. So now that gives me an S. And opposite sides are also parallel. If I highlight, let me just get a little thicker pen over here. If I highlight my parallel lines and my transversal, this angle is bottom left, and so is this one. These are corresponding angles. One's inside the lines, one's outside the lines. They're on the same side of the transversal, and they're in the same spot where the parallel line meets the transversal. They're corresponding angles. And there we have all the information that we need. We can prove the triangle's congruent now by angle, side, angle. And then we could just simply CPCTC the corresponding sides that we need, TK and EH. So I'm just going to abbreviate S and R for statement and reason. So we had parallelogram, DEFG, angle DGK congruent to angle EFH, and that was it. Okay, so the black angles were given. Then we said that GD is congruent to FE. Opposite sides of a parallelogram are congruent. And then we said that GD is also parallel to FE. Opposite sides of a parallelogram are parallel. And then we said angle GDE is congruent to angle FEH. Corresponding angles are congruent when parallel lines are cut by a transversal. You do need to put that it's because of parallel lines, that they're congruent, because corresponding angles is one of those relationships that's only true when we have parallel lines, just like alternate interior angles. You continue over here. It's not too much space. Sorry about that. That's all the information that we need. So we can say triangle GDK is congruent to triangle FEH. And that's by angle side angle. And then we can get DK congruent to EH. And that's by CPCTC, because they're corresponding sides of those congruent triangles. Okay, this one's a really hard one. This one was actually a 6-point question on the Regents exam maybe 2 Junes ago, maybe 3. We have quadrilateral ABCD. AB is congruent to CD. Diagonal AC intersects EF at G. Be careful, EF is not a diagonal. It doesn't go from corner to corner. So EF is not a diagonal, only AC is. And DE is congruent to BF. Prove G is the midpoint of EF. So to prove G is the midpoint of EF, let's work backwards. So G, if G were to be the midpoint of EF, it would split EF into 2 equal parts, EG and GF. EG is the side of this triangle, and GF is the side of this triangle. So if we prove these 2 triangles congruent, we can CPCTC EG and GF, and then we can prove that G is the midpoint if we show it's being split equally. So that's our plan. I'm going to get rid of this because we don't have this to work with. It's what we're trying to prove. But I'll leave the highlighted triangles so we know that that's our focus. These are the triangles that we need to prove congruent. And already I see vertical angles, which are always congruent. So already we have an A. But we don't seem to have anything else. So that's when we have to think about our givens. And we need to keep in mind that all the givens were there for a reason. They gave us that AB was congruent to CD. AB and CD are a pair of opposite sides on this quadrilateral. On the other pair of opposite sides, they give us a piece ED and a piece BF. And there's the information that we're missing. AB is not only congruent to CD, but the last, I'm sorry for that pause, the last piece of given information, I didn't notice it right away because I was reading fast and it was missing the symbol. AB is parallel to CD. I had the symbol missing in my version over here. So AB is parallel to CD. And we do need that. Because now that we know that one pair of opposite sides is both congruent and parallel, we know that quadrilateral ABCD is a parallelogram. Because if one pair of opposite sides is both congruent and parallel, we know it's a parallelogram. Now that we know it's a parallelogram, we can use other properties of the parallelogram to get more information about the 2 triangles in red. I'm going to pause here and I'm going to start writing because we're going to forget what we're saying if we don't start writing some things down now. So We have AB congruent to CD. We have AB parallel to CD. And we have DE congruent to BF. And I'm just writing all my givens down at once. Now I'm going to say ABCD is a parallelogram if one pair of opposite sides are both congruent and parallel. The quadrilateral is a parallelogram. And now that I know it's a parallelogram, I can start to say some other things. Not only is AB congruent to CD, but the other pair of opposite sides, AD and BC, are congruent. Because now that we've proved it's a parallelogram, we can use the properties of parallelograms. That opposite sides of a parallelogram are congruent. And that's helpful because now if I take AD and I subtract off ED, I'll be left over with AE, which is a side of the right triangle. And if I do the same thing on the other side and I take BC and I subtract off BF, I'll be left over with FC, which is a side of the right triangle. And now I'm almost there. I'm also going to put in the vertical angles. And now I need to figure out how to get one more piece of information because I have a side and an angle. I don't think I'm going to get any more side information. Be careful. You might want to say diagonals of a parallelogram bisect each other, but we don't have two diagonals here. We only have diagonal AC. EF is not a diagonal because EF does not go corner to corner. If we had two diagonals, we can definitely say that and use that as our last pair of sides. But I don't think we're going to be able to get a side with what we have here. So let's go with an angle. So we also know that AD is parallel to BC. Because opposite sides of a parallelogram are parallel. And then if I highlight these parallel lines and the transversal that intersects them, you'll see the letter Z. And in the corner of the Z, we have alternate interior angles. So that's angle EAG. And I'll name this one FCG. And I'm going to put here alternate interior angles are congruent when parallel lines are cut by a transversal. And now I have enough information to state the triangles are congruent. And that is by angle, angle, side. And now that we know the triangles are congruent, we could CP, CTC, EG, and GF. Because they're corresponding sides. And this is the plan that we talked about at the beginning. And now we know that G is the midpoint of EF. So always end your proof with the proof statement. E is the midpoint. G is the midpoint of EF. And I can say that's because a midpoint splits a line segment into congruent parts. And that's what we showed in step number 10. We showed that EF is being split into two congruent parts.